This brings us to our next problem. What does a fractional exponent mean? If we raise 10 to the 1/2 power, what does that mean? Now, most of you, I think, are ahead of the game now, and you know what it means, but we can think, if I have a base x and I raise it to some simple fraction, 1 over n, what would that mean? And as always, it's our goal to get the concept clearly in our mind so that we can actually use the concept to solve problems. Following along the pattern we were using before, that the 10 to the 1/2 power ought to mean 1, the neutral number, half multiplied by 10. I'm making an extension of my invented crazy language. If to multiply is to multiply and to divide is to negative multiply, then perhaps there's a meaning for half multiply. If that does have a meaning, what would the meaning be? Well, if 10 to the 1st power delivers us the number 10, then 10 to the 1/2 power ought somehow to give us half that number. We multiply 1 by 10 and get 10. That's basic exponent logic. And if we half multiply, we ought to get halfway from 1 to 10. Now, it would be easy to say that half of 10 is 5. We all know that since we're little children, but that's to assume, again, that we're in an addition world. If we have 10 and you want to cut off a piece of 10 so that when you take that piece and add another equal piece, you get back to 10. Well, that's what we mean by dividing by 2, but that's not the problem we're thinking about now, not the answer we're looking for now. What we want is to cut off some part of 10 so that when we take that part and multiply it by an equal part, when we multiply it by an equal part, then we get back to 10. So if you look at the last line, what we're looking for is the number x, so that x times x is equal to 10. And that is precisely what the definition of the square root is. That's why 10 to the 1/2 power is another way to say the square root of 10. The last line on the screen now is worth taking a moment. Make sure you've got this straight in your mind. That it's easy to confuse 10 to the -2 power and 10 to the 1/2 power, but the concepts are quite different, and that difference is important. Now, following along, what would 10 to the 1/3 mean? Well, that would mean to 1/3 multiply 10, which is to say to find some x, so that x times x times x brings us back to 10. That's just the cube root of 10. And we can have any other root, the 7th root, say, or the nth root. It all just fits the definition we are used to using. We can also use decimals. Decimal is just a funny form of a fraction, which is useful in certain circumstances. But that gnarly decimal, I haven't written out all the repeats, of course, but that is 1/7, 0.14, etc. And if we raise 10 to that power, we would get the 7th root of 10, the number which multiplied by itself 7 times gets us back to 10. So all decimals work the same way. That is, they can replace their fractional equivalents. 10 to the 1/2 power is 10 to the 0.5 power, and that's all the square root of 10. 10 to the 1/3 is the cube root of 10, and that's the same as 10 into the 0.33 repeating power. Which brings us then to the next complication, to an escalation of the question. There's always another question after the one you've settled. What would x to a complex fraction be if a simple fraction has 1 in the numerator? What would x raised to the n over m power, where n could be any number other than 1, 1 or any other number other than 1? What, for instance, would 10 to the 4/5 power be? And for that, we have to do a little bit more thinking. It helps to look back at the logarithmic scale on the graph that we're now getting familiar with. How does this work? Well, I can explain the key. You will see, of course, that the y scale is not even. If you go 1 centimeter up from the 0 mark at the bottom, you've covered a very little bit of the whole distance up to 100%. And if you go 3 or 4 centimeters, you've only gone up to 0.1. But if you go that distance again, then you're at 1. So a much bigger leap you've taken as you go higher on the scale. And if you do that again 3 or 4 centimeters up from 1, you get to 10, and then the same thing gets you from 10 to 100. So it's obviously not even, but there seems to be a rule to it. It's regular, and here's the rule. It's a log scale. It's on what they call the common log, which has a base of 10, and you raise that base to some exponent in order to get the actual number marked on the scale all the way on the left. And the measure of the y-axis is strictly regular for that exponent, which is to say that when I went up through the gradients from 0.1 to 1 to 10 to 100, the numbers weren't constant. We kept switching a larger amount of the numbers, but the distances are equal, and the distances represent equal differences in the power of 10. So when we go from 1 to 10, we cover a distance of a few centimeters, and we cover a certain change in the power of 10. 10 to the what power gives us 1 as a result. We can mark down 1 in the scale. What exponent is that? When we move up to the place where 10 itself is marked, 10 to what power gives us 10 as a result? That's the difference represented by the actual geometric measure between the marks of 1 and 10. And there's the same difference, which affects the exponent on the base 10, as we go from 10 to 100. Now, you might pause the video at this point just to work that out for yourself and to see if you're understanding. For instance, we know that the square root of 10 is approximately 3.16. Where would you find that on the scale? If you look at the hash marks and the numbers, where would you locate 3.16? And switching back to the geometry, the measure up the y-axis, where would you expect to find 3.16 on the distance between 1 and 10? If you had a piece of paper and an accurate ruler and you could mark places, where would you expect to find 3.16 exactly? What method would you use to find it as precisely as possible? Same sort of problem. The cube root of 10 is 2.15. Where would you look for that on the graph between 1 and 10? And if you're getting the concept, then you can see you can have the vital insight that every exponent between, say, 0 and 1 must somehow be represented by some place on the measure of the y-axis, since every distance can be found there, and you can be as precise as possible. You can use whatever fraction of the distance interests you, no matter how complex that fraction is. Everyone must have some value, some exponent with that exact value, no matter how complex the fraction, must result in some actual number.